we will be looking at a simulation and sort of low-level computational software to examine the effects of molecular geometry on the properties of molecules. And we will think about molecular geometry for various compounds that we will simply be given the chemical formula for. So you'll be responsible to actually determine what that geometry is and make predictions about the polarity of these compounds prior to actually building them and measuring these values computationally. And so there's kind of a process that's built in when you're given a chemical formula and you're expected to determine whether the molecule is polar or not. Sounds like a simple question, but you are actually required to go through a process of figuring out what that molecule would look like in 3D space. And before you can even do that, you have to know something about how the electrons are arranged in the structure, and that is what a Lewis structure is. So there's sort of an overall process that we can follow. So we can take the chemical formula that we're given, we can use that to determine how the atoms in the molecule are connected to one another, and that'll help us to know what atom belongs in the center. And from there, we can total up the electrons and distribute them appropriately to get a reasonable Lewis structure. Once we have that, we will know the electron arrangement around the center atom, how many bonds there are, how many lone pairs there are. So the total number of electron regions will help us to know what the electron geometry or the electron arrangement is. Once we have that, knowing how many of those electron groups are considered lone pairs will help us to determine an appropriate geometry for the structure. The geometry is a 3D structure of the molecule, and we can think about individual bonds in that structure, like a carbon-hydrogen bond, for example, and we can try to figure out the bond dipoles involved. And bond dipoles are essentially a difference in electronegativity. If there's a small difference, it's a very small bond dipole, or we might consider it no net dipole between those two atoms. If there's a large electronegativity difference between the two atoms, then we might consider it to be a large dipole. But we'll sort of total all of those up in 3D space to determine an overall net molecular dipole. And the net molecular dipole will help us to determine whether the molecule is polar or not. So the polarity is more of a yes-no kind of question. So if we have a net molecular dipole that's approximately 0, we would say that the molecule is nonpolar. If we have a molecular dipole that is not equal to 0, it's got some larger value associated with it, this would typically be considered a polar molecule. And so you can have like weakly polar molecules and much more strongly polar molecules and so on. But for the purposes of this, it's kind of a yes-no question. When we get to actually calculating values, you can be able to consider relative polarity of molecules based on values that you actually obtain. So let's walk through an example of following this process. So we have a given chemical formula, CH3F, and we can total up the electrons involved in the bonding structure for this compound to determine a reasonable Lewis structure. Now it's important to remember that at this point, we are really only going to consider valence electrons whenever we are drawing a Lewis structure. So if you look at the periodic table based on the groups that each of these elements are found in, you'll remember that carbon has 4 valence electrons, hydrogens each have 1, and we have 3 of them here, and fluorine has 7 valence electrons. So this gives us a total of 14 valence electrons to work with. Based on some simple rules for determining which atom would be the central atom, carbon being lower electronegativity compared to fluorine, and also more capable of making multiple bonds compared to hydrogen, it's the most reasonable atom to be our center atom. So I'm just going to make a star on carbon as our center atom. And so I'll go ahead and draw carbon, and we will draw 4 bonds coming out from carbon to connect the 4 other atoms involved. And I'll just make a note, it doesn't really matter where you put the fluorine in relation to the carbon at any point in this structure drawing process. That's up to you. It will kind of change the angle at which you're looking at the molecule once we get to the geometry position part, but hopefully when you're playing with a simulation, you'll see that you can just turn the molecule around and you can get fluorine to be wherever you want it to be, to look more like the representation someone else drew. Okay, so I've got all 4 atoms connected to carbon now, and if we drew just the bonds to connect each of these, we'll notice that carbon now has 2, 4, 6, 8. If we count 2 electrons in each bond, that is the number of electrons surrounding carbon. That means that carbon's octet is full and satisfied with just those 4 bonds. That's also the case for hydrogen. Hydrogen will fill up with just 2 electrons because it is in that first S energy level. And so its octet is full by just making 1 bond. So the hydrogens and the carbons are all good. The only one that is unsatisfied at this point is fluorine. Fluorine should have a total of 8 electrons around it to have a full octet, and currently there are just the 2 from the bond. And so if we were to go ahead and distribute lone pairs to fluorine, we could see if this actually works based on the number of electrons we have possible to distribute. So we had 14 total, and to count up how many we've used, in the bonds, we already counted 8, and now we've added another 6, so that's a total of 14. So we're good. We've used all our electrons. Everyone has a full octet. This is a reasonable Lewis structure. And in fact, it's the only one you can draw for this compound. Okay, so now we have a Lewis structure. Now what we need to look at next is the electron arrangement. And that is referring to the electrons around the central atom. So we have 4 regions of electrons around carbon. So you could call it the steric number. That is one way you could refer to this. The steric number is 4. So it's 4 electron regions. So that would mean that we have a tetrahedral electron geometry, right? Since none of these electron regions are lone pairs, that means that our molecular geometry is also going to be tetrahedral. All right, so I'm going to draw my tetrahedral molecule down here in the other box. So center atom is carbon, and I'm just going to draw them in circles to make it a little easier. All right, so tetrahedral, you have 4 bonds coming off at angles of 109.5-ish. Depends on the actual properties of the molecule, but you'll see that in the calculated values. Usually you will see 2 of the bonds drawn in plane and 1 drawn with a wedge towards you, 1 with a dash going away. I'm just going to keep my atoms in the same position they were in my original. This is not perfect, so just bear with me there with that. So I've got fluorine and hydrogen, hydrogen, hydrogen. When we're drawing the geometry, it's not super important to draw the lone pairs. It's just understood that fluorine has those lone pairs there. You're welcome to draw them, though. One way that you could represent that is with this type of kind of a lobe with 2 electrons in it. That's how you might see it. It's not super important because the geometry, the key information is what shape it is around the center atom, not around the peripheral atoms. Okay, so now that we know that, the next important thing to think about, so we have our geometry, is going to be bond dipoles. So we need to think about the electronegativity differences between atoms and add up all our bond dipoles so that we can get a net molecular dipole. So here, carbon and hydrogen are fairly close in electronegativity. Carbon is slightly more electronegative, so the way you would draw a dipole would be to draw an arrow towards the more electronegative element and then make the bottom of the arrow like a plus sign for the more positive side of that bond dipole. So because carbon is kind of pulling those electrons towards itself, it means we have like kind of a partial negative charge on the carbon side and a partial positive charge on the hydrogen side. And you don't really need to worry about drawing in these like partial charges if you've already shown the arrow indicating the direction of the polarity. Now it's important to note that these are small. They don't make a large difference in the net polarity of the compound. But we do have a larger difference between carbon and fluorine. And so that bond dipole is pretty big and is pointed towards the fluorine. So that leaves our carbon partially positive and our fluorine partially negative. And so our overall dipole is going to be pointing in the upward direction, and so it's not 0, it's not close to 0. That difference between carbon and fluorine makes a pretty significant impact, so we'll say not equal to 0, therefore it is polar. All right, so that's our prediction. We've predicted what side would be more negatively charged. The fluorine would be more negatively charged, and then that would leave the carbon and hydrogen side more positively charged. Now we're going to look at what we'll be doing using mole calc. So you'll use 2 different pieces of software. One is to look at and confirm the molecular geometry that you predicted, but you'll also use mole calc to get some actual values to analyze in relation to each of your structures. So this is our CH3F molecule that we just looked at. Carbon here is represented in gray, hydrogen in white, and fluorine in green. And this is that tetrahedral geometry. Now the nice thing about using something like mole calc is that you can take these molecules and spin them around in space, so you can get kind of a better understanding of what that shape is like. Once you hit the calculate button, you'll see a bunch of values pop up. So this is taking into account the electrons and all the interactions involved in the molecule. You can get values for the enthalpy and entropy, heat of formation, and so on. There's multiple different tabs at the top of the page, and the other tab that's going to be very interesting for us is the polarity tab. So when you click on that, it will pull up the structure with an electron density map put over it. And so this electron density map kind of shows where the positive and negative regions of the molecule are based on the electron distribution from electronegativity calculations and the shape. And so red will indicate more negative side of the molecule, and blue will indicate a more positive side of the molecule. And just like we predicted, the fluorine is on the more negative side and the hydrogens are on the more positive side of the molecule, so that polarity electron density map aligns with our predictions. And you can actually get values that will tell you something about the relative size of the polarity of the dipole. So the unit of dipole polarity that we'll be interested in are debye, and it's saying for this one it has a 1.6 debye dipole. So you will use that information to kind of compare multiple different molecules to one another, but it's important to know what you're looking at when you actually run these calculations.